Yeah, very nice to be here, and I'm really glad that there is such enthusiasm for machine learning, and that I can speak at my home university about that I have left a few years ago. I'm going to talk about things that I've been doing for the last year and a half at the New York University. It's going to be about applying the most recent advances in deep learning into breast cancer screening. I'm interested in deep learning, and and I'm interested in it because it's amazing. It can do amazing things. These are things that deep learning does is something that most scientists wouldn't believe were possible 10 years ago. And but what is it, right? So let me just give you a quick example that will explain what I consider deep learning. This is a very, probably the most basic deep learning model. This is going to be a neural network, a multi-layer neural network. It starts with an input. And the input in this deep neural network is processed in a series of nonlinear transformations. It has a hidden layer. It has two hidden layers, and then this neural network is outputting this Y. It's a very simple model. As a matter of fact, it's just a composition of functions, and these functions are typically very simple. And this is okay. So this is what I'm going to be considering a deep learning model. So any model that is composed of a series of simple but nonlinear transformations is going to be a deep learning model. And the reason why these neural networks work well is because they can express very complicated functions, but their hierarchical structure is appropriate for many problems. So it's something that this kind of structure you can see in the brains of different animals. That's the features are processed first from very simple ones like here, and then these structures get more and more complicated. And that's basically in one sentence why deep learning works so well. One type of a deep neural network that I'm very fond of is a convolutional neural network. It's designed to work very well with images. What is special about this kind of network is that it has these two types of layers, convolutional layers and subsampling layers or pooling layers. The convolutional layer here is connected in such a way that if you consider this hidden neuron in this layer, it's only connected to these neurons in the input. So what that means is that the neurons in the adjacent layers only have local connections. And also very importantly, this filter here is applied with the same weights on the entire image. So it's a very efficient way of parameter sharing. And the other type of the layer, the pooling layer, is implying a translation invariance of the input. So what that means is that if this was an image of, so this is an image of a house or a church, it doesn't matter whether it's here or here. The network will be able to generalize the different positions independently of where the object is. Okay, so we have this great hammer of learning and deep convolutional networks, and now we could apply it to every type of problem. But unfortunately, the world is a little bit more complicated. So let's consider this diagram for a while. So there are two axes here. So first axis is some kind of abstract difficulty of the task. And on this axis, there is the amount of data available. So what I would consider a difficult task is maybe, I don't want to be very precise here, but let's say, for example, classification of irises with the iris data set is simple, and general artificial intelligence is hard, right? So the kind of problems that deep learning is very good at are somewhere in that corner, right? So it's very good in solving problems like natural image recognition and speech recognition, or machine translation, and I'm sure that many of you have heard of these. Also, very recent example of game playing. Deep learning is doing very well in all of these domains. And these are great, but I think, but it's not really enough, right? So can we use deep learning to save the world? And I believe the answer is likely yes. So one way to do it, to save the world with deep learning, would be to solve the problem of medical image analysis with these kind of tools. And and I believe this is what's going to happen in the next few years. Okay. Another perspective on what problems to solve is I always come back to this famous talk by Richard Hamming. It's titled "You and Your Research," and in that talk, Richard Hamming says that it's primarily important to know what are the good research problems, and you can be brilliant, but you have to pick the right research problems. And the way to consider research problems is again by looking at the difficulty of them. So there are some problems that are very well solved already. For example, building a steam engine is a solved problem. Building a phone is a solved problem. Building TV, etc. And these are, I would say, these are. Okay, I'm not sure if it's working very well. On the other hand, there are some problems that we don't have a very good shot at, right? So solving general AI or teleportation and time travel is something that is not going to happen in the next few years. So somewhere in the middle between these two extrema, there is a line, right? So there's a line, and on one side of this line there is engineering. So there are problems that we already know how to solve, but perhaps we need a lot of effort to put them into practice. And on the other side of this line there is science. And deep learning, in particular, and medical image analysis, is somewhere on that border. And this is what you should. I think this is what I would like to be. So I would like to be on the side of science, but to innovate, but close enough to engineering such that I don't claim that I will solve. So I cannot claim that I will solve general AI in the next few years, but I think it's fairly reasonable to claim that in the next few years, or maybe the next 10 years, machine learning as a field is going to solve a lot of the medical image analysis problems. Okay, so let's zoom into this space. There are many important problems here, but one problem that I'm very interested in is the problem of breast cancer screening. This is a problem of a very large impact for the society. In the US, there are about 40 million exams performed each year. So there's a huge cost associated with these exams. And about 250,000 of the women are diagnosed with cancer. And 40,000 of them, unfortunately, lose their lives to cancer. So if we solve this problem, we won't just be able to do something interesting, but also something that will change the world. Okay, so this is how it looks in practice. So when the person comes to the doctor and wants to have a breast cancer screening, which happens annually, these 4 images are taken. So these R stands for right, and L stands for left. And so these are images. So these are 2 images of the right breast, and these are 2 images of the left breast. And then what the doctor does is they look at these images and try to figure out whether this person will likely have a cancer or not, and it classifies this exam into one of these 3 categories. The category, so class 0, is called incomplete, which corresponds to about 13% of the screening population. This class indicates that the person who came to the doctor might have a cancer and needs additional imaging. Class 1 is negative. It's roughly half of the population. It's these people definitely don't have a cancer, or at least with very high probability they don't have a cancer. And finally, there's class 2, benign findings, which corresponds to the people that have something abnormal about their breasts, which could be a scar or some kind of other abnormal tissue, but this tissue isn't associated with any form of cancer. And these are called BI-RADS. These are called BI-RADS in the United States. Okay. So I said all of this about deep learning, how it can solve everything, and deep learning. But there are still a lot of challenges here. So you need a lot of data to do deep learning because the problems that we want to tackle are very hard, and you can't just solve it with a couple of 100 images. But the data sets that are on the internet are only a few thousand images maybe. And these are the largest data sets for this problem. So the first thing that I've done when I was hired as a postdoc at NYU was I built my own data set. So it's a lot larger. It's 200,000 exams and about 900,000 images, and each image is about 5 million pixels. So this data set is about 4 terabytes right now, and we keep making this data set bigger as people come to the doctor. So this is a really big challenge, actually, because it's a data set of the size that just has not been, at least I'm not aware of a data set of this size considered in deep learning before. Okay, so now I'm going to show you something. So does anybody know what this is? So could anybody tell me what this is? Or maybe could the people who know what this is raise their hand? Okay, so anybody else? Okay, so maybe you can tell your neighbor, not me, right? Okay. So does anybody know what that is now? Okay. So more people. Okay. So more. Okay, just you. Okay. Who knows what this is now? Okay. At this point, everybody should know, right? Okay. Or you should go to, you should check your eyes. So now even the people in the far rows will see. So yeah, so this is a panda. But notice that to tell me that this is a panda, you didn't need this image, right? You needed something. Well, if you were standing to the screen as close as I am right now, you would probably be able, with fairly high certainty, that this is a panda here, right? And this is something very special about natural images, which just simply isn't true about medical images in general. If I show you this, well, I don't think anybody would be able to say whether, what is the medical condition that this person has, right? I think, even I can't tell. This is even a small image for, in the medical world, that would be a very small image. When the doctors look at these images, they have very special screens, and and they look at them in full resolution. And it's very important, actually, because these things that we are looking for are very tiny, right? So this might be these things here, or maybe some structures, some subtle structures that if we resize the image, we will just lose them. So we can't really resize these images, and we have to deal with these facts by processing these very large images, and this is a big challenge for machine learning. And thirdly, this data we have multiple views on the data, which is somehow unusual. So we don't want to make a diagnosis just based on one image, but we want to somehow fuse the information from multiple views and then make the diagnosis. Okay, and I also wanted to say that, because it's still very early in New York, and I didn't have a morning coffee. It will help me if you ask me questions, because that will keep me more awake. Okay. Okay. So this is the model that we used. So this is a baseline model that we used to we tried to solve this problem, and now we are improving on it. So this is a convolutional neural network of this very special structure that where these are the inputs. So this LCC, RCC, LMLO, RMLO. These are input images. These are these 4 views that I've shown you here, and these 4 images are independently processed by what I put here as DCN, stands for Deep Convolutional Network. The output of these deep convolutional networks is concatenated. Then it has one fully connected layer, and there is a classifier on top of that representation. So this classifier is something very simple, like logistic regression. Okay, and this is going to be a zoom into the architecture of this deep convolutional network. This is very similar to what's known as the VGG network, except that because the size of this image is much larger than the natural images that we can't downscale these images, like I said before. We have to alter this architecture in a very particular way. So if you look here, it's customary that when the convolutional layers have a stride of 1, but because we wanted to make this, to downscale this image, we made it 2 by 2. We gave it a 2 by 2 stride, and also this pooling layer has larger kernels that is usually used. And here, this convolutional network also has a larger stride. And the reason why we did that is that by this kind of structure of network, we don't just downscale the image, and we don't lose the information unconditionally, but instead, this network is capable of retaining what's important for classification. Sorry, you have a question? No? Okay. And we use this network we train this network with all of the state-of-the-art techniques. So we do things like dropout, early stopping. We do relative data augmentation. We crop these images randomly. We add noise to them. We share the pairs the parameters in these pairs of columns, so that in reality this network actually this network for these two is the same network. It produces 2 different outputs, but the parameters are the same of in these 2 columns. And when we use Adam to minimize this training objective, because this actually on this scale of the data, a very highly optimized implementation on a very expensive computer takes 3 weeks to train. So if you tried to do this on a desktop, that would take a few years. And obviously we can't wait that long. Yes, please.
How large is the data set?
So the data set is it's about 200,000 examples. corresponds to about 1 million images, and it's about 4 terabytes of data. So the problem that we are hitting here is that at this point you just can't put the images in the memory, and so we have to keep them somewhere. And so one problem is that you can't keep the images in memory, so you need some very efficient implementation to load the data from hard drive in parallel to training, and and that actually requires a very fast hard drive to manage to load this data that quickly. And yes, of course, yeah. So so we specifically use I think the GPU is P100. It's the computer it's IBM Power 8 architecture, so it's much quicker in transporting data from memory to GPU. I was sorry, not Fiano, TensorFlow. Yeah, TensorFlow. But yeah, so and you can only, because of the size of these images and because of the memory that's necessary to store to do forward and back propagation, we can only use mini batch of the size of 4. Right. So it's actually so the training is just very slow because of that. But it's an incredibly highly optimized procedure. Yeah. Sure. So these are X-ray images, okay. So there is some. This is a good question, actually. Yeah. So that depends what kind of augmentations, right? So you have to be very careful because not to erase the information, just exactly for the same reason why you can't downscale the information, the images too much. But but typically the part of the image that is actually important to classification is somewhere in the center of the breast. But it's really hard to exactly locate this part of the image. But if you as long as you do cropping and if you keep this important part of the image in the center of it, even there's some noise, I think it's improving. So I've done some experiments on that, and it's definitely helping. Very small, yeah. It's a very tiny white noise, yeah. Yes. But there's other types of augmentations that you could think of. So translations, so small rescaling, rotations of the images, maybe some elastic deformations of them. I've seen papers where people have done this and it actually helped. Sorry? Changing ratio. Yes. So that's I include this in the rescaling, right? So yeah. So yeah, sure.
Didn't you say that, for example, changing the ratio of the image might affect those small artifacts?
So I think it does to a certain extent, but it certainly does. But I mean, I think just the process. You have to be very careful with the process of interpolation. Because but experimentally, I can tell you that it does help a little bit. So these results that I'm going to show you do not include this, but I have some other results that are just not yet online that where I've tested that a little bit of this helps as well. Okay. Okay. So how does that work? Like I said, there are these 3 classes, and so these are the ROC curves for these 3 classes because this is so what that means is that each time we treat it as a binary problem. So we try to distinguish between the class 0, BI-RADS 0, and the other classes, and we do this for BI-RADS 1 and BI-RADS 2. So yeah, so the way to understand that diagram is that you would like to have, well, so ideally, you would like to have simultaneously very high true positive rate and very low false positive rate, right? So you would like this, so basically what you would like is that this diagram to look somehow like this. That would be the perfect classifier that could perfectly distinguish between the two. This line here, this is what you would get if you had a completely random classifier. So we are somewhere in the middle, right? So we haven't completely solved this problem, but we are making a progress in this. So our average AUC for these three classes is 0.733. And interestingly, actually the class that BI-RADS 0 is the hardest class to learn, and that makes sense because what we are doing is predicting decisions of a doctor, and doctors differ themselves in how conservative they are about pointing somebody to some further examination, because so if the doctor is very conservative, then they would always choose, or very often choose, to ask for more exams to make sure that they are not missing something, because the cost of telling somebody that they don't have a cancer when they do is actually very high, especially in the United States. But other doctors might be less conservative. So it's actually really hard to learn this class. This is the result that shows that you actually do need the image in the full resolution. So here we have. So this is on this axis. There is the fraction of the original resolution. So this is the full resolution is 2,600 by 2,000 pixels, and this is the average AUC. So clearly, you can learn something from the 1/8. You can probably learn something about the image. Just even with this resolution, maybe if you made it even smaller, you could learn something from the pixel intensity only. But the performance keeps increasing when we make these images bigger. There is also the impact of the dataset size. So here, there's the size of the dataset. So we are starting from just 1% of the original data. So that's a fairly small dataset. That will be just 2,000 exams. And that's better than random, and it keeps improving, right? So every time here, every fraction here is roughly doubles, and this is up to some approximation a linear growth, right? So what that indicates is that if we keep getting more images, then we can just simply improve this model by waiting longer to train this. Okay. A very critical thing here to understand in this kind of deep learning is that we cannot just make a prediction, because nobody would like to be operated based on some single number. Yeah. So unlike most applications of machine learning, when the user cares about the prediction, here we actually need some kind of understanding of why this classifier makes the decision, and it's both because we need trust, as well as we hope that the kind of indications of what the model has learned can actually be useful to the doctor. And to do that, we use the entropy of the output for a given x, with respect to different pixels of the image, different pixels in the image, and we take a absolute value of that. So what that means? Okay, so what does this value actually mean? So that means that we want to have high gradient of the entropy with respect to these pixels when these pixels influence prediction. Right? So it doesn't say necessarily which which class it is, but we want to have pixels that give an indication of that. Well, if we change these pixels, then we change the class. Okay, and this is what we get. So this is a case of a person that did have a breast cancer, so this is what a doctor pointed out to us as the cancer, this lesion here, and our model indicated with these red marks that these are the pixels that are important for classification. This is a case of a person who doesn't have a cancer. They have this image belongs to class 2. So these are things that might look suspicious, but they are not associated with any types of cancer. So this is just a biopsy clip that the person who was performing pathology just didn't, the biopsy didn't take it out from this person's breast. And I believe these are just marks. These are just scar marks. And our model again indicated what the doctor thought it should be important. Okay, so what do we conclude from that? This is a first step in this direction of end-to-end breast cancer screening with deep neural networks. So it's important here that rather than just making a prediction about some particular part of this image, we actually want to make a full end-to-end prediction for the entire exam with all images. And it's much harder to learn the incomplete class, 0 than the other classes, like we've seen in these results. And we do need to use the full resolution. And we need a lot more effort to develop architectures that are appropriate for these kind of inputs. And we can still take advantage of more data. Okay, so these are things that I'm currently working on, and I think they will change a lot in our results. So in all of these results that I've been telling you about, we only have the label for the entire exam. So we have in the training time, we have no information about where this suspicious lesion is, and it's a much. If we had this information, it would be much stronger because our model has to currently learn where to look, and then it's deciding whether this is suspicious or not. But this kind of label is just much stronger. We need to have information on whether the person actually developed cancer or not, rather than a prediction of a radiologist. Because only then we will be able to, then we will be just able to largely reduce the amount of people that will need some further examination. And we can use a lot more side information, such as the age of the person, or whether this is the first screening for this person, or whether this person has a family history of cancer or personal history of cancer. We should also be using previous exams for comparison. This is often, so it's often the case that somebody has some structure in their breast, which looks suspicious, but the structure is stable and it doesn't grow over time like cancer does. So that would help us to eliminate a lot of examples that when our network thinks that it might be cancer, but it's actually not. And we need to learn where to look, right? So all of these models, this is much deeper than it sounds. So what I mean by that is standard convolutional neural networks, when they look at the image, they apply the same amount of computation to every part of the image, and this is very wasteful, right? So if we should be able to have models that will first learn where to apply this expensive computation, and then to decide whether this part of the specific part of the image is actually how this influences the classification. Okay, now let's go back to this diagram. Okay, so this is so this was breast cancer screening, which is, as I've shown you from my results, it's we're making progress on this, but it's remaining. We still didn't bend this to this science engineering divide, right? So we're still on the science side with this, but there are some problems like breast density classification that we can actually solve with the models that we currently have. So this is breast density classification is a part of the process of breast cancer screening. So when the person comes to the doctor, then the doctor decides whether this person has fatty breasts, which means that they have very little fibroglandular tissue, or it has maybe a bit more of this, or it's heterogeneously dense, or finally, if a lot of the volume of the breast is taken by this fibroglandular tissue, then this person it's said that this person has extremely dense breasts, and it is important because it's much easier to notice any suspicious changes in the breast of a person that has fatty breasts. So it's part of this process of producing this final diagnosis. And here's what we do: we take the same model and the same hyperparameters. We basically just changed the input. So we just changed the labels to the model. And what happened is very interesting. So we basically, for practical purposes, this problem is very close to being solved. So for all of these classes, we achieved either above or very close to 0.9 in AUC. And on average, we have the AUC of 0.916. And now, okay, we also try to use this paradigm of transfer learning, which is very frequently used in image recognition. So if you've heard about like fine-tuning AlexNet, right? This is something that people routinely do in the industry. They take a network trained on ImageNet, and then they fine-tune it to a particular data set. So we tried to do something similar, except that our network that we started with was not any kind of network like trained on ImageNet, but it was the network that was trained previously. And we tried to do this and to compare how this network learns with very small amounts of data. And because this is an easier task, you don't need so much data, but still, if you only have 1% of the data, it's better to train this network starting from the parameters from the other network rather than to start from scratch. And so these are accuracies. So this is top 1 accuracy. That means, so this is the accuracy if you only consider classification to be correct, if the classifier correctly predicted the most likely class. Top 2 means that we will consider classification correct if one of the 2 most likely classes are the ground truth, and analogously top 3. So for top 3, this is almost perfect, right? So it's very rarely grossly wrong, right? It very rarely classifies extremely dense breast as very fatty. And superclass is the classification between, if we consider 0 and the kind of the less dense breasts, the two less dense classes, and the two more denser classes together. So, but what's important here is that it's unlike ImageNet. This difference isn't very large for small amounts of data, but this network actually learns much faster. So when we were training this model with 1% of data, then we only needed 20 epochs instead of 50. Yeah, so and similarly with 10% of data, we were able to use roughly half of the time to train this network. Okay, and this is comparison to human performance. So I would like you to pay attention here, because this is a pretty complex table. But I think the results here are, in my opinion, very interesting. So what we are trying to compare here is what is the kappa coefficient. So this is a measure of agreement between the labels in the data, our neural network that I was telling about before, a very simple histogram-based classifier, a medical student, a resident doctor, so a doctor who has already finished medical studies but hasn't yet finished the residency, an attending radiologist. So this is a professor of radiology in this case. And what we see here is that, so if we compare them here in this row, right? So our network is actually more consistent than all of them with the data, right? So it's very interesting because the labels themselves are produced by humans, but our network has it's a kind of a super average radiologist, right? Because because in the process of training, it has to somehow reconcile different views of different radiologists, and as a result of that, our model is more consistent with these labels than it's more consistent than the histogram-based classifier, but it's also more consistent than any other human, which is a very interesting result. Because I think nobody was really expecting that. Okay, so what can we do in the future? I believe that a lot of areas of medical imaging will be totally revolutionized by deep learning in the next few years. So we need a lot more work to do this, but medical imaging especially radiology, it just seems like something that computers have to be very good at, and it is because we as humans, our visual system is not very well tuned to these kind of tasks, and it's very time consuming. It's very time consuming to do something like this for a human. But for a computer, it will be just a lot better. It seems very counterintuitive that some problems are actually a lot harder than others. So this breast cancer screening problem is actually an order or 2 orders of magnitude harder than the breast density classification. And there are some problems in medical imaging that are already solved to maybe even superhuman accuracies, like pathologies already. Maybe you have seen some papers about this. But these are these kind of problems are often just a lot easier. And we definitely need new methods for solving this problem. So there's a lot of research that has to be done specifically in machine learning to nail these difficult problems in medical imaging. Something that I think is also very important is that we're currently considering these problems in isolation. So if so I do breast cancer screening with X-ray, so I will just work with these kind of images. But there's only so much that you can read from an X-ray, right? So there are other modalities, there are other imaging modalities that tell you something else about these patients. So there's stuff like ultrasound, when you can look more locally at what's going on, and you can also use MRI. So in the future, we'll just have to use these different modalities to form diagnosis, and we have data to do it. We have data to do it, but it's just we need a lot more both scientific and engineering effort to make it happen. And furthermore, breast cancer doesn't necessarily develop in isolation of other things that are happening in the human's body, and we should be able to consider these things jointly to a large extent. Yeah, we should be using trained learning models to inform science. We should be able to take what we learn in these neural nets and put them back to science eventually. Yeah, this is something that I think is something that's very close to my heart, and I hope to work on this kind of problems in the next few years. Okay, so these are all my collaborators. So these are professors from NYU CS, NYU School of Medicine, and my students. Thank you very much.